Briefer summary, the last two videos. We construct a power function with y factor 4/3. We have our doubling x values. Every y value increases by factor 4/3. Noted that we can't really construct a factor 4/3 because we can't trisect a line geometrically using compass and straight edge. But on a finite interval of the x-axis, including everything up to x equals 0, we can start at the last value within that increment and take 3/4 of that value, and then 3/4 of that, 3/4 of that, 3/4 of that, and we can construct a 4/3 ratio, a power function with y factor 4/3 on a finite domain, but only in a finite domain. If we're in an infinite domain, then we have to have something we can construct, which would include but not be limited to every power of the function p over 2 to the n, where p is an integer and n is an integer, as we've seen repeatedly through the course. To construct an exponential function, well, we have two exponential functions constructed here. They are in a sense the same because you could label the x-axis backwards and get this one. But since we usually like to label the x-axis forward, we do this. We take our arrow to represent our doubling displacement, and we start with some x value, or some y value here. We move over at one doubling displacement, double that y value, double it again, assign that to the next doubling displacement, double that, and so forth throughout. And we get points that we can then connect with a smooth curve that's a good approximation to our exponential function. We didn't need a y-axis to do that, and when I originally constructed this, there was no y-axis, so you can imagine that y-axis is not there yet. Now we can have a negative doubling displacement, so that we start with a value here, and we have to move through the doubling displacement in order to double the y value, which that means we have to move to the left to double the y value. Move again to the left, double, move again, double, move again, double, move again, double, and we get a curve here, which we see as a decreasing exponential. If the x-axis increases in this direction, we say there's a decreasing exponential. The rule is the same. You double the y value every time you move through a doubling displacement. That covers both a positive and a negative doubling displacement, but you do get the two graphs. If you then decide to slap down a y-axis, you can do it anywhere. You still have a graph of an exponential. But if your graph is of y equals b to the x, your basic exponential function, then the y-intercept is going to have to be 0, 1. So if we constructed this decreasing exponential function, this would be 0, 1. If we constructed our increasing exponential function, this would be 0, 1. And then we would have a scale for the y-axis. These graphs are always constructed as unscaled graphs, which is why we don't put a y-axis down when we construct our exponential function. We just get a graph of the general exponential function and know that we can put the y-axis wherever it's convenient. No numbers, no numerical calculations involved in any of these. Okay, simply geometric constructions. Okay, we do the sine function with a reference circle. We divide the angle between 0 and 90 degrees, the x-axis and the y-axis, into 4 equal parts. For each of those parts, we have an angle 0. Well, here's our angle 0. Angle of corresponding to just this angular displacement will be 1 mark, then to this one 2 marks, to this one 3 marks, and so forth. We take the y value at each of these points and associate it with the corresponding mark. Okay, so we go from here to here with this y value, then to here with this y value, to here, and so forth. Now, I explained that in more detail with more words in the preceding couple of videos, but you can, people had no trouble doing this on the exam, so I think everybody understands this. Then we can continue around the circle, and we get the same curve, but backwards here, then upside down, then so forth. And it's very clear how that comes about. Okay, So the algebraic properties that connect with the geometric properties of these graphs, the power function is y equals f of x equals x to the p. Now, f of 2x is the value of your power function. It's twice as far from the origin as the point x, which means that the function has to double, or has to increase by some y factor between these two, and the y factor is just this divided by this, because this is a ratio of the value at x and the value at 2x. And that expression for f of x equals x to the p simply simplifies to 2 to the p. Thus, y factor is 2 to the p. P is the power of the function. Y factor is the y factor you would use in constructing it. And the y factor that you can identify if you have a power function and don't know what the function is. Since the y factor is 2 to the p, it follows from the basic idea of logarithms that not everybody understands, but we have this relationship here. It follows from this relationship that p is log of the y factor divided by the log of 2. So if we've identified the y factor, then we know p. If we know p, then we know what y factor to use to construct the graph. Exponential function is of the form b to the x. F of x equals b to the x, the most basic exponential function. The doubling displacement we symbolize by delta x sub d, change in x as the value doubles. Then f of x is the value at some point x. F of x plus delta x is the value if we move delta xd from that point, so the value has to double, which means that this divided by this has to be 2. And that simplifies using the laws of exponents, which people really need to understand better, to just b to the delta xd equals 2. We could solve this for b in terms of delta xd. We can solve this for delta xd in terms of b. Solving for b, we just take the reciprocal delta xd power of both sides. Again, you really need to know those laws of exponents. And we get b equals 2 to the 1 over delta xd, 2 to the reciprocal of the doubling displacement. If we want to solve for delta xd, we use this logarithmic relationship, this logarithm relationship. Then again, you don't have to understand any more than just to understand that this is equivalent to this. And we get delta xd is log 2 over log b. So if we know b, we know what doubling displacement to use in order to construct the graph, or having constructed the graph, we know what the numerical value of the doubling displacement is, and now we can scale the x-axis. For the sine function, the period is from here to here, the change in the horizontal coordinate of the graph. That's the period. A is called the amplitude. It corresponds to the radius of the circle and is, of course, equal to the distance from the x-axis up to the maximum value, or from the x-axis down to the minimum value. Now, if the period is taken to be 2 pi, which corresponds to 2 pi radians for reasons that you need to fill in when you get to that point, and the amplitude is 1, in other words, radius of the circle is 1, then this is the function y equals f of x equals sine x, the mathematical sine function.